So welcome everyone as you keep joining. So thank you very much for joining this, which is our 12th webinar within this ECE Data Science Distinguished Series. Before presenting our speaker today, let me briefly go over some logistics. If you have any questions, you can write them in the Q&A chat, and towards the end of the talk, we're going to select some of those questions to be answered by your speaker. During the talk, I'll also monitor the Q&A in case there's any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of the questions towards the end. The talk will also be recorded and uploaded to our YouTube channel for future access in case you want to review something or recommend it to a friend or colleague. So that being said, it is my pleasure to present today Dr. Maya Gupta as our distinguished speaker for the data science seminar. Dr. Gupta received her bachelor's degree in EE and Econ from our very own Rice University back in 1997, and her PhD degree in EE from Stanford in 2003. At that point, she joined the Department of Electrical Engineering at the University of Washington as a faculty member, where she stayed for just under a decade until 2012. From 2013 to 2020, she led the Glassbox machine learning R&D team at Google Research, developing and deploying new ideas in constraint machine learning to make products more accurate, interpretable, safe, and fair. Dr. Gupta has also founded 5 companies and is now the CEO and co-founder of Didero, a new kind of search engine. So she's not going to be talking about this today, but I'm quite curious about it, so I'll ask her about this later. So she received several awards during her time in academia, including the Office of Naval Research Young Investigator Award for her work in sonar statistical signal processing, and the PCASE, which is basically the most prestigious Young Investigator Award. This was, if I did my homework correctly, in 2007. So I take it that you got to meet President Bush back then, right? So since the award is handed by the president himself. If not, so we can discuss this later. So it is always great to have Rice alumni giving talks. So like Mike Rabat a few weeks ago, and today Maya Gupta. As I mentioned, Dr. Gupta's track record include time in academia, research in industry, entrepreneurship. So basically something for everyone. And this broad range of experiences surely gave her a very unique viewpoint to tackling problems. So I'm very much looking forward to her views on this talk in particular. As a side note, Dr. Gupta founded a wooden jigsaw puzzle company that I had a lot of fun exploring the website yesterday. So Maya, thanks for visiting us today. We're very happy to have you here, and the floor is all yours.
Thank you, Santiago, and thank you and Rich Bernick for organizing this. It's really a delight to be back at Rice. It's been a number of years. While I'm sad not to be there in person, being there virtually means the humidity is not as bad, so that's a good thing. So yeah, I'm excited today to talk to you guys about shape constraints. This is a very old idea in statistics that we found is really important to making machine learning work more robustly, and I'll show you how it can make machine learning more fair, more safe, and more accurate. This is all work that I did at Google while running the Glassbox machine learning team. And so it's joint work with a number of fantastic engineers and researchers there. And it really, the work I'm going to talk about sort of spans 7 years of work. So there's a lot here, but we're going to keep things a little high level and focus on the ideas. Okay, we're going to find out if we can change slides. Okay, let's start out with an example. This is a very simple problem for machine learning. We've got only 2 samples, or 2 features. And we're going to try to predict whether a law student will pass the bar. And we're going to have 2 features here. We'll have the undergraduate GPA and their LSAT score, how they did on the standardized test. And there's about 19,000 training samples here. So for a 2-dimensional space, you'd think you have plenty of training data with 19,000 training samples. And this is what the DNN looks like if you just train a 2-layer DNN. You get this sort of surface for what is the probability the student will pass the bar. And so you might realize this is very flexible. The DNNs are wonderfully flexible, and this is fairly accurate. But if you look closely, you'll realize that there's something very bad going on, which is that there's certain places where if your GPA increased, we would lower the probability that we thought you were going to pass the bar. So this red arrow shows you a couple places where if you go from a GPA of about 2.8 to 2.9, and your LSAT score is around 20, we're actually going to reduce our prediction. So you can imagine. This is kind of nonsensical, right? And you can imagine if you were trying to give out scholarships for law school, and maybe you're looking at people's GPA and LSAT, and we're using this information. Let's predict if they're going to pass the bar, and if they have a high score, we'll give them a scholarship. You can imagine this would feel very unfair to some people because they're being penalized for having a higher GPA. So this is one of the things that you get when you have overfitting with machine learning. It's just what machine learning can do, but it's a very particular kind of overfitting that causes these problems. And like most overfitting problems is coming in part because we have sparser data in some of these regions. So even though we have 19,000 training samples, which sounds like a lot in 2 dimensions, that doesn't mean it's spread evenly over the space. And so we still can get these sort of overfitting problems. And it means that some experienced people are going to have this very bad experience, even if it's not the dominant thing that's happening. Okay, so what I'm going to talk about today is shape constraints and an open source toolbox that we developed at Google called Tensor Flow Lattice that allows you to force these kind of monotonic relationships. So it allows you to say upfront that the GPA should only have a positive effect on your prediction of whether you're going to pass the bar. And your LSAT score should only have a positive effect on the prediction of whether you pass the bar. And so you can see these green lines mean that, you know, for any GPA, as your LSAT goes up, you only go from a darker to lighter color because your prediction only gets better. And so you see the surface here is not that different, but it smooths out those problem areas that the DNN has, where it causes this sort of unfair problem where it's penalizing people with higher GPAs and higher SAT scores. And in terms of test scores, these things are actually statistically significantly indifferent in terms of their test accuracy, even though the plots look quite different. And part of that is because most of the training and test data is IID, and so most of it is up here in this top right corner where most people are sort of passing the bar. So most people are easy to classify. But this is still an unfair problem that you get with the DNN that we know that we can fix by taking account this prior information that we have, that we know how GPA and LSAT should affect the score, and enforcing it in the model when we train it. So a lot of times people talk about interpretability, and I really think that interpretability is kind of, it's often done too late. They'll train a DNN and then they try to interpret it. But you can see even in this 2D case, how hard it is to interpret that DNN. So you can imagine if we have 1,000 features or 1,000,000 features, how hard that is. And it's sort of too late because the DNN's already done something really, really unsensible and unreasonable and really unfair. So we want to design in what we need for interpretability, such as these sort of shape constraints like monotonicity. Okay, so mathematically, what is a monotonicity shape constraint? Well, it says that for any feature z that I want to have monotonicity on, so here z is our GPA. If I have any other features x, then if z gets bigger, then the function has to get bigger. And if this is a continuous function, then it just says I have to have a positive first derivative. So my slope has to be positive everywhere with respect to GPA. So this would be the constraint that we would put on for GPA. And then we could put a separate constraint on for the LSAT score. And visually, these constraints just look like what you see on the right-hand side, that along any of these arrows, the function should be increasing. Okay. I'm not going to talk much more about fairness specifically this talk, but if you'd like to see a lot more on the subject and how these kind of monotonicity constraints relate to fairness and what kind of fairness, we have an AI stats paper that just came out called Deontological Ethics. Deontological ethics sounds really complicated, but deontological ethics are actually the really like common everyday ethics, like first in line should go first, or you know, you shouldn't kill people. Those are all deontological ethics. So you can see more about that in that paper. Okay, so in general, what we look at with machine learning is that you start with some noisy training data, you train something, and you get an ML model. And today's ML models work really pretty well, as long as the training data and the test data look the same. But as we just saw, even though the DNN and the TF Lattice models were equally accurate, one of them made a lot more sense and was a lot fair. So it's not sort of enough to just look at accuracy these days. And what we'd like to be able to do is take our domain knowledge, take policies like we want to make sure that getting a higher GPA doesn't hurt you, incorporate those into math, and then incorporate those into the training so that we can produce machine learning that better models reality and better models what we want from our machine learning so that we can control our AI. So there's a lot, this is sort of a big space here, right? You know, we could go Bayesian, but we're not going to go Bayesian in this talk. A lot of times when people talk about prior knowledge, they want to talk Bayesian. Here we're going to talk about prior knowledge in the sense of shape constraints, things like, hey, I know GPA should be a positive signal. I'm not going to let my model go and penalize GPA. So here we're going to focus on the subset of domain knowledge and policies that we can impose with these shape constraints. And we just went to an example of monotonicity. Some of the other shape constraints that we've done a lot of work for and that you can get out of the TF Lattice toolbox are diminishing returns, complementarity, dominance, and unimodality. And I'll talk through some of these today. Okay, so let's just look at another sort of visual example. Here we're just going to be in 1D because it's so much easier to visualize. But of course, many of your models are going to be 30 dimensions or 1,000 dimensions. Here we're going to predict how far will people go for a cup of coffee. So we might have some example users and we send them to different coffee places at different distances and we ask them how happy they are. And so we get some training data, which are the cyan dots here. And then we can go and fit a curve. And this is stylized, but you can fit a DNN that looks a lot like this. And what you'll see is that this DNN is having this sort of same problem. It's very flexible, which is awesome in some regards. It's very good at memorizing, but it also is not monotonic. There are places here around 1 kilometer where you go further and supposedly people are going to be happier. So if you were using this function to score coffee shops, you would end up with some very unhappy users in practice. Okay, so if we force this model to be monotonic, we're going to get almost as good a fit to the data. Because we're constrained, we won't get as good a fit to the blue points here, but we'll get almost as good a fit, and we'll get a much more sensible model that will behave predictably. And what's more important is it behaves predictably at the extremes. So if you look at the unconstrained model, let's say that we got this data maybe from some city like Seattle, these are sort of coffee shop distances, but we've got a little bit of an uptick out in that 10-kilometer range there. That's probably not going to bother us if we look at other data from Seattle, because we're hardly going to see any training samples from that part of the space. But if we now try to use this model in Montana, if we shift where we're using it to a different set of data or different distribution like Montana, where coffee shops are farther away, or even parts of East Texas, we're going to have a lot more data coming up in that far tail of the space, and we're going to get hit by this non-monotonicity out here in the tail. So these are good reasons to prefer monotonic models if you know a priori something like, hey, the further you send people, everything else the same, they're going to be less happy. We should tell our model that so it doesn't have to try to figure that out from the data. We can just tell it a priori, make sure you're monotonic in this dimension. Okay, and then we might want to go even further. We might say, well, look, we know that the way people think about distance is with the diminishing returns. 2 kilometers is a lot worse to you than 1 kilometer, but 11 kilometers and 10 kilometers don't really matter that much. So there's this diminishing returns effect to distance that we know many people have, and so we can tell the model that a priori and force it to be both monotonic and convex. We've got some external noise that we're fighting with, but hopefully it will be over soon. So you can read more about the sort of diminishing return shape constraints and how we can do that in multiple dimensions in her NERPS paper from 2018. Okay, so how are we imposing these kind of constraints on models? Well, the way we're doing it is by using a different function class than most people are used to using. So a function class is things like linear models as a function class, decision trees are a different function class, neural networks are a different function class, SVMs are a different function class. Here we're using a function class called lattice models. And this is both very old and kind of new. So I'm going to talk you through it. Some of it's going to seem familiar, but we've definitely stretched what the statisticians used to be doing quite a ways. So those of us who are older remember that in the back of our math textbooks, we had these literally lookup tables. If you wanted the logarithm function or the sine function, you would go to the back of your textbook and you would look it up in the time before calculators. And so lookup tables have been very, very old, used to represent functions. And when you have something in between the entries in a lookup table, you just interpolate. So what a lookup table is basically a piecewise linear function. It's a representation of a piecewise linear function. And the great thing, at least in 1D about a piecewise linear function, here I've got these knots here that tell me what the pieces are for my different inputs that I'm interpolating linearly, is that as long as I make sure that the lookup table values, these values on the y-axis are increasing, I know that this function is increasing. So the constraints to get monotonicity are very simple. I just need the adjacent lookup table values to be increasing. So when I have multiple features, the simplest thing we can do is put this together in what we call a calibrated linear model, which is a special case of a generalized additive model from Chibshani and Hasty. And what we're going to do is we're going to take each of our inputs. You can have thousands of them, whatever you want, millions. And for each input, we'll put it through one of these piecewise linear functions. So the ones that want to be monotonic, we can constrain this to be monotonic. And the ones who don't, we don't need to constrain it. And you can have a piecewise linear function that isn't monotonic. And then we can just bring those together in a sum. So that's, you calibrated the features by putting them through this nonlinear transform that you get to learn. And then you have a linear sum. These models are very easy to interpret and explain. Rich Karuna from Microsoft has been pushing something a little similar because of its explainability. So in many ways, these are great models. Let's take a look at an example of that. So here I have 4 features. This is from the public Diamond data set. And this is what the different piecewise linear functions look like. for the different 4 features. And so you can see that we can look at this and we can say, oh yeah, the way that the model is responding to the carets and the diamond is very linear. The way it's responding to the clarity has a sort of sigmoidal function. It really only cares about things in the range of 1 to 3. And the way it responds to cut is sort of logarithmic, right? So we can very easily interpret what the model has learned in these calibrated linear models. So while they're easy to interpret and explain, the problem is they're not arbitrarily flexible. And in modern machine learning, there's really 2 types of models. Ones that are not flexible enough and ones that are flexible. And again, we find that we do want models that are arbitrarily flexible, like DNNs. Big enough decision trees can be arbitrarily flexible, random forest, etc., because then you can fit anything. So these calibrated linear models, really nice if you're not super focused on accuracy, but if you want super focused on accuracy, you need a more flexible model. So how do we get more flexibility? So what we're going to do is we're going to keep this calibration layer because it's really easy to interpret. It really helps us debug things, helps us know how the model is transforming each of the features. But then instead of fusing the features together with a sum, we're going to do something more flexible. But we'd still like to guarantee those shape constraints like monotonicity or diminishing returns. So in order to do that, we're going to extrapolate what we were doing before to multiple dimensions. And we're going to build multidimensional lookup tables. So this is an example of a 2-dimensional lookup table here on the right. So it's a 2 by 5 grid of values covering 2 inputs, input 1, input 2. And wherever you come in, you just interpolate from the cell, the lookup table cell that contains you. And you can see here that we can, if I have enough lookup tables values, I can fit any kind of arbitrarily flexible function I want as long as it's bounded everywhere. So this is enough to give us really good flexibility. This is some work we did actually back in University of Washington with Eric Garcia in 2009. Okay, and so here again, now I can also impose those monotonicity constraints because I still have this highly structured function. So if I want to make it monotonic in input 1, I just need to make sure that these lookup table values are always increasing anytime I go left to right. So that's true here. It's very easy to check. It's easy to constrain when training. And if I want to make it monotonic in input 2, I just need to make sure that my lookup table values in this direction are also increasing. And that's also true here. It's easy to check and it's easy to constrain. So now I can make these multi-layer models where I have more flexibility. So here's just an example. I'm coming with 2 features, x1 and x2. Each of them goes through those calibrators, the piecewise linear function that non-linearly transforms them. And then the second layer, I'm going to fuse them together non-linearly with this 2-dimensional lattice, this 2-dimensional lookup table that's interpolated. And this is the kind of function that you can get. You can see it's arbitrarily sort of flexible. And it's a little hard to tell here, but this function is not monotonic. In this direction, it's going sort of up and down, but it is monotonic in this input. Along any of these lines, this function is guaranteed to increase. So what we're saying is that by creating these multi-layer functions with multi-dimensional lookup tables, we can create whatever flexible functions we want and still get these kind of shape constraints. And then compared to something like decision trees, what's nice about this is that these are smooth functions. So we don't end up with the piecewise constant problem that you get with decision trees. So yeah, so as I was saying, this function is actually monotonic in this direction, but not in that direction. And with the functional form, it's easy to test that and to train that. Okay, so we've taken this kind of far. So in terms of what you can get out of the Tensor Flow Lattice toolbox and how you can get these shape constraints, you can certainly get shape constraints with just linear models. You just need to make the coefficient positive. We showed you how to get shape constraints with calibrated linear models, where you sort of calibrate each feature first. And these calibrated lattice models then infuse those features non-linearly with multidimensional lookup tables. Those multidimensional lookup tables have a lot of parameters. They don't scale well if you have a lot of features. If you try to make one lookup table with 10 features or one lookup table with 20 features, you're starting to talk about a lot of parameters. So what we usually do in practice is actually make an ensemble of those calibrated lattices, much like you would have an ensemble of decision trees, but these are smooth and are easier to constrain. And then more recently, we worked on just sort of deeper models. So you can layer these things and you can layer them also with linear layers and create sort of arbitrarily deep lattice networks. Here's an example, just architecture of a deep lattice network. I'm just showing a few inputs because again, it's hard to show a lot of inputs, but you might have 3 inputs that you think should have a monotonic effect or a positive effect on your output, things like the GPA and the LSAT score. And you might have some other inputs that shouldn't have a monotonic effect, like maybe what state people are in or what day of the week they're taking the test. And then you can force that monotonicity through all of these layers. So this first layer here is a linear embedding layer. So linear functions are easy to make monotonic. Each of these little squares here is a calibrator, which we know we can make monotonic. Then we have an ensemble of multidimensional lookup table layers, and we might have some other calibrator layers, we might have some other linear embedding layers, etc. We might fuse that all together with a multidimensional lattice at the end, and in this way we end up with say 9 layers that we can train using SGD. Okay, so that's kind of at a high level. Yes, you can do the code-wise, what's really happening underneath. Well, the nice thing about these lattice models is that all of these shape constraints that we're talking about, we can impose with linear constraints. So the lookup table parameters theta are really those lookup table values themselves. And so as I said with monotonicity, we just need to make that certain lookup table values are bigger than others. And so we can capture that all with linear inequalities. And so we do our normal minimization of empirical risk over your n training samples. You're going to minimize your loss between your function value and the label. And then you additionally have these linear constraints on that. And this is part of what's so nice about this function class is that you do get this highly structured notion means that all of your math is also highly structured. So in terms of engineering and actually solving this, at Google, I think we engineered this from scratch about 5 times different ways in C++, in compiler optimized code, in Tensor Flow. The open source version is Tensor Flow Lattice. There we use a batch stochastic gradient descent and we use projections with Dijkstra. It's not the fastest, most efficient thing that you can do, but it works well with TensorFlow. And TensorFlow in general is not the fastest, most efficient thing you can do, but it's nice and open source and easy to use in Python. So this is a pretty good solution that is publicly available. Okay, so we talked about 1D constraints like monotonicity and diminishing returns. I now want to talk about some multidimensional shape constraints, and this is more of a new idea. So imposing monotonicity goes back to like Barlow in 1952 and isotonic regression, but trying to impose multidimensional shape constraints we haven't seen done by anybody else, but we've found it to be very useful in practice. So this is, you can find out more about this in our ICML 2020 paper. And I'm going to talk about a few different multidimensional constraints. The first one is dominance. So you might have a bunch of features, but you might know that one of your features, say feature 5, should really be more important to the model than feature 14. And so we often do post-hoc analysis of which features are more important in trying to understand a model. But sometimes we know a priori, or for policy reasons, we want to say, look, model, you should really treat feature 5 as more important than feature 14. And so these tools allow us to do that. So some examples of this that we do a lot is trying to use recent data and saying that the recent data should be more important to the model than older data in time series models. Now, of course, there's cyclical effects where that's not always true, but this is often something you can impose. Similarly, if you've got sort of web stores, there's sometimes different quality of people coming by. People who are actual customers and buying things are going to be more valuable, and their information should be taken more strongly than people who are just viewing or visiting the website. And just in general, this is the birds in hands versus birds in the bush kind of mentality, that sometimes you know which features are more important. So how do we codify that? In the paper, we talk about a couple different ways to codify that idea that a feature is more important. Here, I'm going to talk about one of the easier ones to understand, which is just monotonic dominance in terms of just slopes. So here we might say the function should change more when you change x1 than it does when you change x2, and they're both going to be positive changes, so they'll both be changes greater than 0. For a linear model, this would be really simple. You would just say that your coefficient beta 1 had to be greater than beta 2, and they should be greater than both greater than 0. But in nonlinear models like lattices, we can still impose this by imposing the right relationships on those lookup table parameters. And similarly here, you can see here, if you're in the feature space, this x1, x2 feature space, if you take a step in this direction, you want the function to change more than if you take a step in that direction. That's all this is saying. And you want that to be true everywhere in this space. So here's an example of that. Here we're predicting weekly sales. This is a public data set, so I think it's in the paper. And here we're just imposing the constraint that recent sales matter more than old data sales. Okay, so on the left here, actually let's start on the right, which is our trained MSE. And we look at this black model is the unconstrained model. And what you see is if you add in more features about the past week data, the trained MSE goes down. So the model is fitting better the more features you give it, right? And that's how it should be. But if you look at the test data, the more features about the past that you give it, the test MSE is actually going up. All of this great look over here is all just overfitting. On the other hand, if you constrain these models, either to be monotonic or to have this monotonic dominance, and range dominance is another variation of what I'm talking about, your trained MSE doesn't get that much better. It gets very slightly better as you add more features about the past weeks, but your test MSE doesn't go down. You get very little gain, in fact, out of this extra data, but you do get a little bit of gain. But the good news is you reduce all that overfitting and you make sure that the model is doing the right thing. And basically here, there's very little information in the past weeks is what happens. Okay, a second type of shape constraint that we can apply on multiple features is complements. So you might know that feature 3 and feature 4 are complements. When I was at Rice in Texas, I did an econ degree as well as electrical engineering, and one of the famous examples of complements at Rice in economics was guns and ammo. We don't talk about that as much in California though. But other notions of complements is, let's say you want to predict how fast you can solve COVID in a population. Well, that might be a function of the number of vaccine doses, but also the number of nurses. And you know that those are complements. You need both of those to get good behavior. Similarly, if you're trying to predict wait times at a grocery store, your cashiers and cash registers are complements. And then one of the ones that's important in the internet is that click-through rate. What is the probability that someone is going to click on something? Trying to predict click-through rate for the future, you can base it on click-through rate in the past, but you also want to know the number of impressions. Because if your click-through rate is only based on a couple clicks or a couple impressions, that's not as promising as if you have a lot of impressions, then you know that you can trust that click-through rate more often. So all these complements, we can say a priori, hey, we identified that these are complements and the model should treat them as complements, and we can enforce that through shape constraints. So here's an example of the math for that. We call this an Edgeworth constraint from the economist Edgeworth, who studied complements a lot. And basically we're just saying that the derivative as it varies in x1 should change more as it varies in x2. So let's see that pictorially. Here's an example where I have two features. One is a rating, let's say a star rating, or a rating on a academic paper. And the other is a rate of confidence. So what we're seeing here is that if the rate of confidence is low, then whether the rating is low or high, we're positive in the rating, we're monotonic. We think better ratings are, represent, say, a better paper. But we're not gonna, because the rate of confidence is low, the slope is not that big. Whereas if the rate of confidence is high, then a negative rating matters more, it's more negative, and a positive rating matters more, it's more positive. So this twist of slope of saying, yeah, we should trust the rating more as the rate of confidence increases is exactly this complements relationship that you see in the math over there. And again, if we have these multidimensional lookup tables, we can impose this by imposing it on the lookup table parameters themselves. Here's another example of that, which is measurements and how precise they are. So this is just sort of a general way that you might apply this. You might have some measurement that should be positive related to whatever you're trying to predict, your label, and then you know how precise that measurement is. If the measurement is not very precise, it's a noisy measurement, then it shouldn't matter what you measure because it's noisy, you shouldn't trust it that much. But if your measurement precision is good and you see this is a precise measurement, then you want to trust it more and your function should vary more because of that. So here's an example where we're predicting app installs. And here we'll start out with an unconstrained model. And then we'll add in a constraint just to be monotonic. And we'll make it that's monotonic on the number of reviews. So we'll say the more reviews an app has, the more likely we think other people will install it. And the higher the star rating the app has, the more likely we think other people will install it. And the lower the price is, we think more people will install it. So we're imposing those three monotonicity constraints for this monotonic line here. And then additionally, we'll have this other line, monotonic plus Edgeworth. We're also constrained that the star rating and the number of reviews should be complements. So if there's a star rating is basically an average, right? So if you say, well, the star rating is 5, but there was only 1 review, we're not going to take that as seriously as star rating is 5, but there were 100 reviews. So I've got two sets of numbers here. In this first set, we have the IID split. And you see that the train MSE, as you add constraints, goes up a little. It's sort of the same here, but it goes up a little because we've added constraints. So we're not allowing the training to find the lowest MSE because we're forcing it not to overfit. We're constraining more with these extra constraints. So that's that regularization action. On the test MSE, we do see this getting a little worse as well. So our unconstrained model actually is also having the lowest test MSE. And here we actually paid a little bit. Here we got a little bit of a win here. And a lot of this is just sort of some of the noise here, but it's not hurting us that much. What's important here is that this is IID data. So here we've split the training set IID, which means that the training and the test data have the same distribution. And if we now look at a non-IID split, we see a very different effect, which is that we see a stronger effect from the regularizer. So the trained MSE still going to suffer a little bit from adding the constraints because you constrain the training not to find the minimizer, but your test MSE now going down when you have these additional constraints. And we see this sort of effect a lot, which is if you have the same distribution of training and test, you just don't need as much regularization. But when you have non-ID data, then you need more regularization, and the regularization helps you more. And this kind of regularization is nicer than other kind of regularizations because it represents beliefs and reality, or beliefs about reality, rather than just arbitrary regularizations like dropout or smoothness. So dropout and smoothness will help you protect against domain shift or non-IID samples, but all you're doing is saying, yeah, I'm just going to hedge my bets and be less certain. Here we're saying, hey, we have some prior information, or we have some beliefs, or we think the model will be more interpretable if we add this in, and then we get that value out of the regularization that comes from the interpretability that we get there as well. So a lot of people worry about, we're using a lot more AI in the world, can we understand what it's doing? And this is one of the nicest ways to be able to summarize to people what the model is doing. So here I can if I just train an unconstrained model, I have literally no idea what it's doing. But with this monotonic model, this monotonic and Edgeworth model, I can explain to people that, yeah, you know what, this is going to respond positively to more reviews. It's going to respond positively to more star rating. It's going to give you a bonus if you reduce your price. It's going to give you more power if you've got more reviews for that star rating. This is all very sensible, and it makes people feel like they understand what the model is doing and that they can trust the model to behave better. Okay, we're going to kind of flow back out here. So the key thing that we're looking at is that when you have all this noisy training data, and the world is full of really noisy training data, you train it, and then you get this ML that works really great, particularly on IID data. So yes, you get great responses out of DNNs, but particularly when the training and the test distributions are the same. Now the problem with that is that we're getting cut off here, but reality is just not IID. Anytime you train a model, you're going to test it if you're using it in the real world on data that is from a different distribution. If you've got a new product that you're launching, your early customers are going to be different than your later customers. Your just early adopters versus later adopters are going to be different distribution. If you're doing any sort of time series modeling, the future is different than the past. Everything you're doing is necessarily shifting around. And so it's very important that we look beyond IID data. Unfortunately, so much machine learning is dominated by academia, and in academia, it's easiest to use IID data, and it's sort of clean and nice, and you can do more analysis. But the reality of machine learning really is that you're dealing and using non-IID trained and test sets, and so this kind of regularization that lets us extend better to non-IID test sets is very important. So we've talked here about these different kinds of shape constraints, and that they provide this regularization that's robust, not just to overfitting within a distribution, but to overfitting between distributions, as I was saying about the non-IID set. And it also creates these models that you can trust because you know what they're learning. So you can have two models that are equally accurate, but if you don't have one that's constrained, you don't necessarily know why it's getting that accuracy and how it's going to respond tomorrow. When you have these kind of constraints, you can explain what the models are doing. And as we talked about in the LSAT example, these kind of constraints allow you to impose certain kinds of fairness, these deontological ethics. And then while people talk a lot about interpretability, one of the things that we saw in practice in machine learning is that what we really needed is debuggability. So we wanted to make sure that the model was doing something sensible, and we wanted to be able to debug it. And these kind of constraints mean that you sort of know what the model is doing, you can form better hypotheses, and it's easier to test hypotheses. So we felt that these shape constraints have helped a lot with debuggability. Okay, but this is just one way that we can take domain knowledge and policies and try to impose them on the training. There's a few different things that you can do. Shape constraints is just one. We have a whole other set of work on what we call rate constraints, which is another aspect of making models fair, and work on slices. And there might be, and there's of course the whole Bayesian idea, although I've never figured out how to impose Bayesian ideas in practice. But there's probably lots of other ways to get this high level goal of saying, look, we do have some domain knowledge, we have prior knowledge, we have policies that we want the AI to respect. How do we incorporate those into the training? So I think this is a very important direction for society and for AI. And I hope the rest of you will think a bit more about it as well. Okay, so everything I talked about is available in this open source library. There's really great tutorial documented stuff, so you can just go through and play with some of this yourself and build on it if you want. And these are some of the papers that I talked about today. And I'll open up for questions. Thanks.
Perfect. Great. Thank you, Maya, a lot for the presentation. Very interesting. I'm sure a lot of people have a lot of thoughts, and also they are probably just willing to go on and code a bit. Probably the people that are more code-oriented just play with the library. So let's open the floor for questions. Remember, you can write your questions in the Q&A box. We actually have, let's see, so we have one hand. Yeah, so David Scott, so feel free to ask your question actually just by talking. You'll need to unmute yourself first.
Yes. Okay, hi, can you hear me?
Yes.
Yeah, hi David.
Hi, thank you, it was a great talk. In fact, I am very much interested in this monotonicity, and I just have a question that I wonder if you have, if at the end of the day you can tell me when you've fit all the monotone pieces. I have two questions. So if I go back to, say, your diamond example, which was what, 4-dimensional, I think?
Yeah, just a calibrated linear model in 4 dimensions. Yeah, here we go.
So I guess my question is that you're fitting a monotone piece over a hyper rectangle, I guess, at the end of the day. And do you have any who wants to know if this model is good for, 4 values of the parameters, whether there's any support in the hypercube for that? In other words, you'll get a prediction, and the question is there a lot of data there, or maybe you're off in a corner somewhere? Is there any way of knowing where the data is relative to what you're interested in?
Yeah, so in this, so the monotonicity constraints are not distribution dependent, right? So they're forcing things to be accurate everywhere. One of the things that we do in our toolbox and in all of our models is that we set the knots for the piecewise linear function based on the distribution. So like here you see in the depth that it's pretty flat, and then there's kind of a lot of activity here in the pieces. So there's a lot of pieces here in the middle. That's because we've picked the knots based on quantiles of the training data. So just this, I know that a lot of the training data was right in this region, or I wouldn't have all these pieces. Whereas here I can see that because this is pretty linear here, probably most of the training data was sort of around here, and it was having trouble fitting the monotonicity, so it ended up only fitting something very, very sparse.
So is this good? So it's monotone even where there's no data, I guess is what you're saying.
Yeah, we make sure that everything is guaranteed everywhere over the space. And again, you can do that because it's just a lookup table. So if we go back to this very simple example, everything that comes in between 1 and 8 is going to, have to be monotone because we just covered the whole space.
So
now,
so in general you extrapolate horizontally or linearly, or it sort of depends.
Yeah, so I think the question you ask is, what if my input is 9? It's off my chart, right? It's off my lookup table. So you could extrapolate linearly. We don't. We extrapolate with constants. We clip, but we generally do set our input range to cover what we think of as a reasonable input range that we expect to ever see. So usually our 1 and 8 are sort of far enough out that we don't expect to see much data outside of that. And if we do, we figure we don't really know much about that, and we tend not to extrapolate because it's so dangerous to extrapolate into regions where you have really sparse data. If we had more data there, then we'd have more knots there, and it wouldn't be outside of our region.
And if you wanted a confidence something, what would you be able to give that?
Sorry, what?
If you wanted a confidence interval or something for a prediction, would you be able to provide that?
So you'd have to layer that on top of this, right? So this, like most machine learning, is just sort of an average estimate, right? Because when we're training this thing, we're just training one function f to minimize the average loss, if we use squared error loss, for example. So in itself just gives you a mean or expectation. If you want any confidence intervals, you could train an additional model to get like the variance of a Gaussian if you want to make a Gaussian assumption. Or we also have some work on quantile regression using monotonicity constraints that does give you the full non-parametric distribution. It's a really beautiful paper, but it's under review for NIPS right now. So
where did you say this paper was again? It was really nice. Thank you.
Sorry, the one on the quantile regression or this work?
This work, yeah.
This work, I covered kind of a lot in this talk. One of the sort of basics to see the math and see it in glorious detail here is this JMLR paper. It's a nice long journal paper from 2006. on the Calibrated Interpolated Lookup tables. And then the papers since then are sort of richer, more multi-layers, giving you access to more features, et cetera, because at a place like Google, we need to be able to handle lots and lots of features and not be restricted like you are with one multidimensional lookup table.
Thank you so much. It was very nice.
It was nice talking to you again, David.
Mm-hmm.
So thank you. So let's move to some of the questions we have here in the chat box. So Rich Varnick says, great talk. You might have talked about this, but is monotonicity both necessary and sufficient for your results to hold? I'm not sure if, yeah. So if Rich, you want to follow up on that, feel free to unmute yourself if you want. Yeah.
Oh, I can unmute. Yeah, just, hey, Maya, great, super interesting. Yeah, just wondering if this is just one of the ways that you can do what you're talking about, or whether it's like the only way. Does that make sense?
Sure. So if you want monotonicity, like let's go back to this first example of the LSAT here. If you want monotonicity, you have to force this mathematical relationship. If I want to say that, look, you're never going to get penalized by this model for having a higher GPA, I have to enforce that relationship. But how I enforce that relationship, I have a lot of options for. So here we've used these lookup tables, but I could use a different function class. You can make DNNs that are monotonic. It's a more restricted function class than normal DNNs. So you lose a lot of the flexibility, and then you have to do a bunch of tricks to kind of get the flexibility back with these skip levels and stuff. So we kind of have not spent a lot of time in that direction because it's a bit unwieldy and a lot harder to interpret. You can also make decision trees that are monotonic. And of course, you can make linear models that are monotonic. And I believe you can make SVMs that are monotonic, although it might depend on the kernel definition. So, if you want this constraint, you need this constraint, but then you can impose that on different function classes.
Mm-hmm. Okay. Great.
Thank you.
So here we have another one. So Ginevra Allen. So she's asking, how can we trust interpretations of ML models if there are multiple models, perhaps with several that are interpretable, that can make the same predictions? That is, do you worry about overfitting with your interpretations, or if your interpretations are not unique or identifiable? I guess if you have a bunch of ways of actually doing interpretable models, do you have a way of, a posteriori maybe saying which one is better? Yeah, your thoughts on that? And Ginevra, I'll allow you to discuss further if you want. Yeah. So I'll unmute you here. Please go ahead, Maya.
So I think there's a few different questions there. One is that sometimes we'll have a series of models that are acting on something, and so we might need to have constraints on each of the models on the component. Another is when we have an ensemble of models that are maybe making a set of decisions. What we find in practice is that we usually like to have all the models be sensible, and then if you get the ensemble, you still have a sensible result. But the more you compose models, the more you may get overfitting. So if you have like 10 models that are acting together and each of them have some constraints, that's more constrained than you really need for the final decision to be right. But it's hard to make the final decision right without putting those constraints on each of the component models.
Mm-hmm. Yeah, so I was thinking, now we move to another question, so we do have time. So I was actually thinking in some of the schemes that you show, right, we have kind of domain knowledge going into the model, and then you will have an output, right? So it's something like this scheme over here, right? So I was just wondering, is there a way of having like a closed loop here, right? So the output model then tells you something about the domain knowledge that you started with, right? So are some of these the things that you're assuming truly sensible or not?
Yeah, I think that's a great question. And we played a little bit around with that in this multidimensional shape constraint work, like with this predicting app installs. Here this is not a Google product. With Google products, we usually know what features should do what. But here we didn't because it's public domain. But we're able to do sort of hypothesis testing. So you can say things like, well, let me try forcing a monotonicity constraint and see if it hurts me if I put on this feature. Or let me try seeing if these guys are really complements or if this feature is really dominant. And if it starts to hurt the model accuracy a lot, then you know that constraint is either not represented by the data or not represented by reality.
Yes.
You can kind of do some hypothesis testing to understand how these features are really interacting if you want to kind of use that as an interpretability tool.
Right. And in doing that, is there other things than MSE that would make sense? I mean, I understand thinking in terms of performance would make sense, but are there any other metrics that would make sense to kind of test those kind of hypotheses?
Well, often you have classifiers, so you're doing this in classification accuracy. classification accuracy, really only depends on where the decision boundary is. And in a lot of real world models, even when we're classifying, the decision boundary will move around. So we might deploy a classifier, but we might use a different decision threshold for certain target audiences or different countries, because some places you want to be more liberal with your decision than others. And so I think it's often a bad idea to just look at classification accuracy. When you look at MSE, you learn a lot more about what your model is really doing everywhere in the space than just the decision boundary. But I think I didn't really answer your question. You're asking, are there other metrics? I'm not sure.
Maybe metrics that are directly related to the assumption, right? So here is kind of an a posteriori thing, the prediction, right? But something that how much it violates your assumption, this or that, right? So I was thinking something like that.
Yeah, well, and the other thing I would say is that we look a lot at Google at slices, and this is sometimes talked about in terms of fairness. So you'll say, well, how is this model doing on, say, if I'm looking at a model that goes all over the world, how is this model doing on US traffic? How is it doing on Japan traffic? How is it doing in Nigeria? And making sure that there's no slices that are particularly bad or good. So you could have a model that's 1% better overall, but if it's a lot worse in some country, you might not want to launch it.
Yep, well, it's perfect. Thanks. So here we have another question. So Mitch Rodenberg asks, so do these types of constraints allow you to gain stronger guarantees on the training of a neural network? For example, does it alleviate the presence of local minima in the loss landscape, right? So not in the function afterwards, but actually in the landscape with respect to the parameters.
Yeah, that's a fun question. I don't think I've looked at that enough to have an opinion, but I think that's an interesting question to look at, is what do these loss landscapes really look like? And that again might look matter a bit of what loss you're using. I'm a big proponent of MSE, minimizing mean squared error, and I think that goes back to my electrical engineering roots, because we care a lot about squared error and Gaussian assumptions. But I find that a lot of machine learning researchers like logistic regression, and I think there's theoretical reasons for that. But logistic regression tends to cause you more trouble. It tends to make your function values much more extreme, and I believe may cause you more of these sort of local minima and other type problems. So it's a little bit of a digression there, but I think that's all a very interesting question. And we've learned some other stuff recently about how SGD versus things like Atom and other accelerated versions can change the landscape to have better local minima or more broad local minima. So I think there's a lot of interesting work to be doing in those areas.
Okay, thank you. Feel free to write more questions. I'll send a few of my own since we still have time. So think in terms of hyperparameters, and this actually tied a little bit with part of the question of the first question that you got, right? So let's say that I sit down, I try to use this this library, right? So before, I had to decide, let's say, how many layers and how width these layers are. So now it seems like maybe I need to decide, how many points do I need to do this in this, these hyper rectangles, and maybe also how to distribute this. But you already talked that it had to do with the data. So what decisions do I need to make to put something like this in practice?
Yeah. So if we do something as simple as the calibrated linear, where you just have like these piecewise linear functions, you have to decide how many key points you want. And so we have rules of thumb for that, but generally we do validate those questions. And when you get to the bigger models, when you're using like an ensemble of calibrated lattices, you're going to decide what order all these multidimensional lattices. A very default model size for us is to make an ensemble of 50 models, where each of those models is a calibrated lattice on about 8 features. And that usually is good for, if you have, 20 to 200 input features or so. So it's a lot like decision trees or a random forest model in that sense of picking sort of how much do you want in the ensemble. As we build more deep lattice networks, what we found is that the best results are really from sort of hand architecting these based on the domain knowledge. So we'd often have, I think one of our models had about 5 or 6 layers, but each layer was really very meaningful in what it was doing and why it made sense, and it led to certain debuggability and interpretability that we could do. And we were able to see huge gains over the DNN in that case, where you just kind of throw it and train it and hope for the best with your hyperparameters, by being a little bit more thoughtful about what the layers meant and what was happening in each layer, and adding that debuggability in. And in particular, it was the sort of thing where the average results, if you look overall, were just a little better. But on slices of data and slices of traffic that mattered, you were getting these huge gains, because it's very hard to do well on some of these more sparser slices of traffic. And the DNN just would sort of ignore them and focus on the big, more frequent slices of traffic and overfit those, rather than use these constraints to make sure it was learning things in the right way and learning the right things rather than just memorizing. But yes, just like any modern machine learning, there's going to be some hyperparameters, and if you take a look at the tutorials in Tensor Lattice, they'll sort of walk you through what we sort of think of as the defaults. But it never felt like a big problem to choose those or a lot of sensitivity to those.
Okay, and then you talked about the discretization of the lattice being proportional to the data, to the density of data to begin with.
Yeah.
Is that something can you talk a bit more to that? So do you end up like choosing this thing randomly with a distribution that is similar to the distribution of the data that you start with, or is there something more going on there?
Yeah, so when you have let's just look at this piecewise linear function in the bottom right here. You have some inputs, you're going to decide where to put your knots, and you're going to decide where to put your values, and that's going to define your piecewise linear function. You could train where you put your knots. You could move your knots around in the X space to kind of try to improve your accuracy. We've thought about that, but we never did it because it makes the whole training much more non-convex and nasty. And instead, what we've always found useful is to put the knots in the X space based on the quantiles. So if I have 10 pieces, I would put the knots at the 10 quantiles of where the training data was. And that means that each of these values that's getting trained is getting represented by about 10% of the data. So we know that we can kind of trust what those values are because they're seeing a good amount of data. And if we do 20 knots, each would represent sort of 5% of the data. So we found that to work very well and remove some of the problems that you get when you let, like if you try to train k-means clustering or something, you get these sort of degenerate problems. And so I worry if you try to train the knots, you get degenerate problems. But statisticians have looked at a lot of these issues, and there's probably a lot more that you could do there. It was just never, we felt it worth digging into for us.
Right. And a similar point would be probably with how you choose the interpolator, right? So here, linear sort of makes sense, and it's probably the first thing that you would think of. But did you guys think about doing some other interpolator between these points? Did it become too hard to fit, not enough gain? So how does that work?
Yeah, so actually worked on some of these models before I got to Google at the University of Washington. And there, one of my graduate students, Eric Garcia's thesis, spent a lot of time looking at different interpolators like cubic splines. These are basically linear splines that we're using here. What he found is that with higher order interpolators, you can get a little bit more accuracy if you sort of smooth these with higher order splines. But we never found it really mattered in practice at Google because you can just add more training samples, or you can add more knots to your piecewise linear function. And the piecewise linear function gives you a lot more control, and it's a lot faster to evaluate because you have this very simple thing. You just got to pull out the two knots and interpolate them. So probably you can do better, but the practical reality is like, well, it's just sort of not worth focusing on. When you go to the multidimensional lookup tables, here what I'm showing you is a bilinear interpolation. So each of these grid cells here is getting interpolated. You can kind of see sort of this fake line that's happening here, because if you're on this side of the cell, you're getting interpolated from these 4 points. When you go to this side of the cell, you get interpolated from these other 4 points. Here we're using bilinear interpolation, which is a generalization, and multilinear interpolation, which is a generalization of just linear interpolation. In a lot of models, we use something else, which is called simplex interpolation, which is also the same as the Lavash extension if you do submodularity, which is much faster. Instead of being 2 to the d, it's O of d log d, but it's a little less smooth. So there is a lot more here you can talk about in terms of what kind of interpolations do you use, but we're generally driven by the technology. So if you're in C++, you can do the Lavash extension interpolation, and it's faster and it scales a lot better. In Tensor Flow Lattice, we haven't really been able to do a great job of it. We have to use the multilinear interpolation, which is smoother. It's just a little slower than it all.
Okay. Perfect. So that was a very complete answer. Thank you. So if there are no more questions here, so what I'll do is thank you, Maya, very much for the talk again. Very interesting.